Hi everyone, in this video we're going to talk about continuity. So what is a continuous function? So here are two examples. You probably recognize the graphs. The first one is y equals x cubed, and the second one is y equals x squared. So these are considered continuous functions. So what does it mean to be continuous? Graphically, it means that there are no breaks, no holes, no jumps in the graph. So another way you can think of it is that if you were to draw the graph, you would never pick up your pen or pencil from your paper. It was just a continuous movement, right? There are no jumps or breaks in the graph. So conceptually, that's what it means to be continuous. So let's try looking at a function. So if I have the actual function, so in this case, I want to graph y equals the absolute value of x from its piecewise definition. Now remember, what is the piecewise definition of the absolute value of x? The absolute value of x is defined to be x if x is greater than 0, and negative x if x is less than 0. So x if x is greater or equal to 0, and negative x if x is less than 0. So this is the definition of the absolute value of x. So when we graph it, that means we will graph x first. So the line y equals x when x is greater or equal to 0. So I would graph that starting at 0, 0, and graph y equals x. So this gives us this line. And then when x is less than 0, we graph y equals negative x. So what does that line look like? And that is the line with slope of negative x, negative 1. And so that's how we get the v. Now, is this a continuous function? It still is a continuous function, right? Because I will start graphing minus x, and then I will get to 0, 0, and then start graphing y equals x. So even though it's defined as a piecewise function, there are no breaks or holes in the graph. So this, we will say it is a continuous function. So let's try another example. Determine whether f of x equals this function is continuous in its domain. So when it asks you to determine whether something is continuous in its domain, it's really important to know, well, what is the domain? What is the domain of this function? So it's defined when x is less than 0 to be x squared. X squared is normally, the domain is all real numbers, but we're just taking the x's that are less than 0. And y equals x plus 1, the domain is also all real numbers, and so we're taking that part when x is greater than or equal to 0. So together, they make up the entire real line. So the domain is all real numbers. So it's asking us, is it continuous on all real numbers? So, well, first let's see. We have, as we said, right, x squared is a continuous function. So y equals x squared is a parabola, which is one of the graphs I had before. So this is continuous. Y equals x plus 1, it's a line, which is also continuous. So where do we have a risk of this not being continuous? Is when those pieces are put together, right? So we have a risk of it not being continuous at 0. So possible risk of break, jump, or hole at x equals 0. So let's look at the graph. When x is less than 0, we look like the parabola x squared, only to the left of 0. So I'm going to try to freehand it over here. So I'm going to have my parabola. Okay, let me try something different. So this is my y equals x squared. I had to pause so I could draw it better. And then y equals x plus 1 for x greater than or equal to 0. So this is a line with y-intercept about 1 and slope 1. Now, when x is x squared when x is less than 0, notice that not including 0. So over here, I should have an open circle because we're not including 0. For y equals x squared. Now for the y equals x plus 1, we do include 0. So at 1, we're going to include that point, and then we draw our line. So this will be y equals x plus 1. So now, is this function continuous? So if you were going to draw it in one swoop, right, I would be drawing my parabola, but then I have to pick up my pen from the paper and draw the y equals x plus 1. So then this function is not continuous, right? F of x is not continuous because it has a jump. And so that's called a jump discontinuity. Okay, so this will be an example of something that is not continuous, and this one, y equals the absolute value of x, is continuous. There are no breaks, there are no jumps in the graph. Let's try another one. For this next example, so let f of x be that function. Determine if f of x is continuous on the entire real line. And then b, determine if f of x is continuous in its domain. Okay, so then these are two, even though they look very similar, they are asking totally different things. So on the entirely real line means we're looking for, is it continuous? This is my abbreviation for continuous, CTS, on minus infinity to infinity, right? Is it continuous in its domain? So if it's asking you is it continuous in its domain, what do you need to find? Find the domain. Because when it's asking you if it's continuous in its domain, it's asking you, is it included for all the values where the function is defined? So let's look at this. So f of x is x squared minus 5x plus 6 over x minus 3. I see that I have a denominator. And what do we know about denominators? Denominator can't be 0. So that means that we don't want x minus 3 to be 0. So x can't be 3. So the domain of this function is all real numbers except x equals 3. So the domain is minus infinity to 3 union 3 to infinity. Okay, so now let's see. Is it continuous on the entire real line? No, right? Because at x equals 3, there's no y value. We just found a domain. So when x is 3, we are not going to have a y value for that. So since 3 is not in the domain, we won't have a y value for it. So we can say, in fact, x equals 3 is a vertical asymptote. So f of x that looks like this has 3 is not in the domain. And oftentimes when I see that things are in the denominator, it makes me think that I do have a vertical asymptote, but is this really a vertical asymptote? Let's explore. Notice that the numerators are quadratic, so let's factor it out. So this factors into x minus 2, x minus 3, right? Two numbers that multiply to positive 6 and add up to negative 5, negative 2 and negative 3. And so that means that I can cancel this out. From our previous sections, we know that whenever this happens, this creates a hole in the graph. So x equals 3 is not actually an asymptote. It is a hole in the graph. So that means that f of x, the graph of f of x looks like y equals x minus 2, except there is a hole at x equals 3. And how do you find the value of that? You take the limit. And so that means that this graph is going to look like y equals x minus 2 with the hole at, 3, 1. If you plug in 3 in here, 3 minus 2 is 1. So the y value, the limit is 1. Right? The limit as x goes to 3 of x squared minus 5x plus 6 over x minus 3. Doing our limit rules here will be the limit as x goes to 3 of just x minus 2. once we cancel that factor out, which plug in 3, you get 1. So this has a hole at the point x is 3, y is 1. So let's look at the graph. So this is what the graph looks like. And so this is the graph of this function, right? So this function looks like, I know I keep saying that, I sound like a broken record, looks like y equals x minus 2, but it has a hole at 3, 1. And so as we saw, right, the domain does not include 3. So now that we have some work and some idea of what's happening here, we can answer the questions. So for part A, is f of x continuous on the entire real line? So that means, is it continuous from minus infinity to infinity? No, right? It has a hole at the point 3, 1. So it's not continuous on the entire real line. But is it continuous in its domain? Right? Its domain excludes 3. So if you don't look at 3 in here, is it continuous? Yeah. So in its domain, you can graph it and stop at 3, not include 3, and then is continuous on the rest of it. So for part A, we can say f of x is not continuous on the entire real line, on minus infinity to infinity, because there's a hole in the graph. So we say it has a removable discontinuity. So removable meaning that you could redefine the function to fill it in. Right, so I can say let g of x equal the function, so our f of x above when x is not equal to 3, and we can define g of x to be 1 when x is equal to 3. So what is this going to do? It's going to take this f of x and graph it with the hole in there. That will be the when x is not equal to 3. And then when x is equal to 3, what I'm going to do is then I'm going to come in and fill in that hole at x equals 1. So that's why it's called a removable discontinuity, because it essentially can kind of like remove the little hole or plug it back in. So it's not continuous on the entire real line, and this is how we would make it continuous. So this was a side note. For part B, is it continuous on its domain? Yes. So f of x is continuous on its domain, which was minus infinity to 3 union 3 to infinity. So be very careful about how the question is worded. Right? Is it asking you, is it continuous on the entire real line, minus infinity to infinity? Or is it asking if it's continuous in its domain? Because if it's continuous in its domain, you just have to look at the domain of the function and decide whether there are jumps or breaks on that part. So not including any values that the domain excludes. So we're going to go over what does it really mean to be continuous algebraically. How do you check it? So we're going to go into our checklist for continuity, but I'm going to do that on the next video, part 2 of continuity functions.